All right, so we're looking at continuity day 2, and our objective for today is to investigate IVT. So you're going to learn what does IVT stand for, and you're going to learn that it is one of those important concepts in calc that never goes away. So we are, again, talking about continuity. So continuous functions take on properties just like algebraic functions. If the functions f and g are continuous initially, then the following combinations of those functions will remain continuous at different points. So if f and g are continuous, you can add them, subtract them, multiply them by a constant, or divide them, and their continuity will remain unchanged. The only concern for continuity would be dividing by a function and making sure that function does not equal 0 at any value. So again, continuous functions can remain continuous if you add, subtract, multiply, divide. Okay. Composite functions are fog and goth. So composite functions are continuous as well. So properties of continuity apply to composites. Composites are thus continuous at every point at which they are defined. For example, if f of x is continuous at x equals c, and g of x is continuous at x equals f of c, then g of f of x is continuous at x equals c. In other words, the limit as x approaches c is g of f of c. So we can also apply a limit to composites. Theorem 7 in our textbook says that if f is continuous at c and g is continuous at f of c, then the composition of g of f is continuous at c. So we can show that example or theorem by taking a function f and constructing two functions from it. So f of x is equal to the absolute value of x sine x all over x squared plus 2. So what we're going to do is break f of x down into two functions. So we're going to turn f of x into h of x and g of x, where h of x and g of x are also continuous functions. So we want the composition of these two functions to equal f of x. So we're going to create our two functions, h and g, so that g of h of x is equal to f of x. In order to make that work, we're going to take the outer function and call it g. So in the case of this problem, the outer function is the absolute value. So we're going to say that g of x is the absolute value of x. So if g is the absolute value of x, h is going to be representative of the inside function, which is 8x sine x all over x squared plus 2. And we know that sine of x is continuous. X is linear, so that's continuous. And then x squared plus 2, well, x squared plus 2 is a quadratic that is continuous. And since the denominator can never equal 0, it is also continuous. Because there are no values for x, that will make the denominator 0. So we've said that g of h of x is equal to f of x. And we said that g of x is equal to the absolute value of x. We know that g of x equaling the absolute value of x is a continuous function because we know that the absolute value is continuous. And then again, what I basically just said is h of x is really equal to x times sine x times 1 over x squared plus 2. And we know that x is continuous because it's linear. Sine x is continuous. And 1 over x squared plus 2 is continuous because there's no values that will make the domain negative. Therefore, by the properties of continuity, h of x is also continuous. And so we can say in finality, by function composition theorem, f of x is continuous. So again, calculus is the math class in which we start writing. We're going from solving equations to being able to say why and how we can solve those equations. We're going to talk about where did that come from? Why is that true? And a big part of that is the intermediate value theorem. This theorem is a statement that holds true for calculus and will be applied at least once on your AP exam. The intermediate value theorem states that a function y is continuous on a closed interval. So that is important. It has to be a closed interval. A function y is continuous on a closed interval. AB takes on every value between f of a and f of b. And there is a slight, this should be a, and that should be b. In other words, if y naught, and y naught is the same as n, if y naught is between f of a and f of b, then y naught will equal f of c for some c in AB. let's dive deeper into what that is really saying. So the first part of the statement, a function that is continuous. So functions that are continuous on intervals have properties that make them useful. So continuity was the beginning of this unit. Continuity says that there are no holes, jumps, or vertical tangents. The intermediate value theorem for continuous functions is the reason why the graph of a continuous function on an interval cannot have any breaks. So it is this single unbroken curve. If we have a beginning and an end, so our graph starts at A, and here's f of A. It ends at B, here's f of B. We know that to get from point A to point B, this function does not break, bend, etc. It's continuous. I can draw my pencil between them. So what this is saying is that from the beginning f of A value to the ending f of B value, every value on the range exists between them. The intermediate value theorem guarantees every value on the range between f of A and f of B exists. That's what IVT says. So it's saying if f of A is equal to 10 and f of B is equal to 1, that every value from 1 to 10 exists at some number C on the domain. So it's saying every value from 1 to 10 on the range exists, and it exists at least one number C on the domain from A to B. The application of the intermediate value theorem is more important than the intermediate value theorem itself. The theorem is a statement of truth. The application of that statement is important. So you may get a question like, is there a real number x that is exactly one less than its cube? So what we say is for this number to exist, it must satisfy the equation that x is equal to x cubed. Well, we know that we can rearrange terms around an equal sign. So we know that that's equivalent to x cubed minus x minus 1. So what we could do is start picking values of x. The obvious starter choice is always 0. So x of 0 is negative 1. X of 1 is 1 cubed minus 1. So 1 cubed minus 1. Well, what's 1 minus 1? So you get 0. 0 minus 1 is negative 1. So that didn't help. I haven't really moved anywhere. X of 2. So now you have 2 cubed minus 2 minus 1. Well, now you get 8 minus 3, which is 5. So now my graph, we have at 0, -1, at 1, -1, but at 2, we jump to 5. So I have no idea what this graph is doing between 0 and 1, 1 and 2. What I do know is that the graph maybe connects them. I know it connects them. It's a continuous function because x cubed minus x minus 1 is a polynomial. And we know that polynomials, we know that polynomials are continuous. So if a polynomial is continuous, I know that this is continuous. Therefore, by IVT, I have a continuous function. So my f of a is like x1. My f of b is x2. So I can say by IVT, since x of 1 is equal to -1 and x of 2 is equal to 5, and the function is continuous, then there exists some point C between one and 2 such that f of c equals 0. And then that would mean that at that point, x would equal x cubed minus 1. And if you really want to know what it is, the value is like 1.3247. Comma 0. So again, the application of the intermediate value theorem is the important part of it. It's being able to use it to justify why or how something exists. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. So again, very similar application to what we just said. So in order to apply the intermediate value theorem, we need to show a few things. We need to show that it is a continuous function. So we're given that it's a polynomial, and by definition, all polynomial functions are continuous. So the first thing we're going to say is because f of x is a polynomial function, we know that it is continuous. Because it is continuous, IVT applies. So therefore, the intermediate value theorem applies and guarantees f of x will equal 0 at some value c because f of 0 equals -1 and f of 1 equals 2. So by IVT, it guarantees f of x will equal 0 at some value c, because at the beginning of the interval, we're at -1. At the end of the interval, we're at 2. So it means that between -1 and 2, we have to have a 0. It has to cross the x-axis at some number. Good? Does that make sense logically? Can you like kind of understand and see like what's happening? Again, it's saying if you have a graph, you have 0, -1, and you have 1, 2. So that means this curve, it might cross multiple times. It might cross one time, but it has to cross at some point because it has to get from the beginning to the end, and it has to go through there. I cannot get to that upper point at 1, 2 without crossing the x-axis, which is where f of x equals 0. This is an example of an AP multiple choice question. So it says the function f of x is continuous on the interval from -3 to 9. So once again, we're told continuity. Continuity implies the application of IVT. So it says the function is continuous on the interval. We're told that when f is -3, it's at 0. So oftentimes when I'm given problems like this, I roughly sketch a graph. And that f of 9 is -12. Which of the following would be a correct statement concerning the existence of a value c by the intermediate value theorem? So it means that my domain is -3 to 9. So any multiple choice option that's not in that domain for x is out. So immediately I can eliminate multiple choice option A. A is not guaranteed by IVT because 12 is not in my closed interval. So right away, I can eliminate multiple choice option A because 12 is not in my interval. So now I have to consider the range. The range is from -12 to 0. The range is from -12 to 0. So now I can look at the multiple choice options, and any value in which the range is outside of -12 to 0 is not guaranteed by IVT. So even though f of -1 is between -3 and 9, 13 is way down here. So I'm not guaranteed that -13 exists. So option B is out. All right, -2 is in my domain. -10 is in my range. Therefore, letter choice C is guaranteed by IVT. Because once again, 8 is in my domain, but 1 is outside my range. So letter choice D fails because it only meets one of the two requirements. Okay, example 5. This kind of relates back to the assignment from yesterday, but it's something important and I want to touch upon and work on. A lot of calculus is being able to construct problems that are general. So we're being asked to find A and B that make this piecewise function continuous. So the definition of continuity says that f of A has to exist. The left-hand limit has to equal the right-hand limit at A, and then that the limit has to equal f of A. So K of X has 2 points of concern, the breaking points. These graphs are going to be discontinuous at a breaking point. So we need to make the breaking points continuous. So we're going to find the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. The limit as x approaches 2 from the left is going to come from the top part of the function, x squared minus 4 over x minus 2. But what happens if you plug in 2 to that equation? 2 squared is 4, 4 minus 4 is 0, 2 minus 2 is 0, we get 0 over 0, which is the indeterminate form. So what we have to do is manipulate x squared minus 4 to be x minus 2, x plus 2 over x minus 2, which simplifies to the limit as x approaches 2 from the left of x plus 2, which tells me that the limit as x approaches 2 from the left is equal to 2 plus 2, or 4. Now we're going to look at the limit as x approaches 2 from the right, which would be to ax squared plus bx plus 3. So when we find the limit, we find it through direct substitution of the limit value in for x. So that means that this is equal to a times 2 squared plus b times 2 plus 3. So that's 4a plus 2b plus 3. So again, in order for something to be continuous, the left-hand limit has to equal the right-hand limit, which has to equal the function value. So that means that 4 has to equal 4a plus 2b plus 3. Well, that's not exactly something I can solve for yet. So let's try taking the second limits. Let's look at the limit as x approaches 3 from the left. Well, now that's a times 3 squared plus b times 3 plus 3. So I get 9a plus 3b plus 3. So that's the left-hand limit of 3. The right-hand limit at 3 is 2 times 3 minus a plus b. Or 6 minus a plus b. I don't know why it's like double writing. So again, in order for this to be true, the left-hand limit has to equal the right-hand limit. So that means that 9a plus 3b plus 3 has to equal 6 minus a plus b. So both of these statements have to be true for the function to be continuous. So let's rearrange these terms to look like a systems of equations. And let's solve for a and b using our systems of equations way back from Algebra 2. So we're going to make the top equation 4a plus 2b, because I always got x and y on one side and the number part on the other. So that'd be like subtracting 3 from 4, so you get 1. So we have 4a plus 2b equals 1. For the second equation, we'd add a, so we get 10a, because 9 plus 1 is 10. Subtract b, so you get 2b. And then subtract the 3 to be with the 6, and you get 3. So I have 4a plus 2b equals 1, and 10a plus 2b equals 3. So if I subtract the bottom from the top, or the top from the bottom, four minus 10 is negative 6a. 2b minus 2b is 0. 1 minus 3 is negative 2. Divide both sides by negative 6. And now you get a equals a positive 1/3. To find b, we just plug it back into any one of our equations. So personally, the easiest one to plug it back into is probably the 6 minus a plus b. But again, it doesn't really matter. You can kind of plug it in anywhere. If we plug it in up here, we eventually can simplify and we get b is equal to negative 1/6. So again, you just plug it into equation 1 or 2 to solve for b. And you could actually plug it in here or here if you wanted as well. So did we do what it asked? It said find the values of a and b that make k of x continuous. So we did make this statement true. If I were to go back now and plug a in wherever a was and b in where b was, my limits would equal each other. If I plugged a and b into the equation up here and here, you could plug in 2 to the top and 2 to the middle, and they would equal each other. Plug in 3 here and 3 there, and they should equal each other. Algebraically, that was challenging. I've said it 100 times in calc. Calc isn't hard. The algebra in calc is now hard. Calculus concepts themselves make sense. It makes sense why the left-hand limit has to equal the right-hand limit. It makes sense why the top has to equal the bottom. What's hard is being able to correctly solve a system of equations that has a and b and get to the point where you know you need to solve that system. Are we good? Okay. So oopsies, I have to clear that. Your homework is in the textbook as well as a worksheet. Those need to be submitted by midnight on Sunday. The worksheet is really a critical concept for this unit.